So, so we're happy to have Benjamin Kriaa, sorry, who works with Benjamin Favier. He's ending his second year PhD, and I have trouble with names. Sorry.
It's fine. Thanks for the introduction, and thanks for having me. So I'm going to present mostly experiments, which I'm doing in the lab to model some precipitation-driven flows, rain and snow, which are happening inside planets. And actually, I'm going to mostly focus on the phenomenon of iron snow inside planets. So, okay. So the starting point with iron snow is that we observe that some small rocky planets like Mercury generate their own magnetic field. We believe it is generated by dynamo, which means that there are motions at the center of the planet, moving charges, and this creates the magnetic field. Very well, but we just don't know where these motions come from. And so we believe iron snow is an appropriate candidate. So to be clear and simple, I just pick one single example to present, which is Ganymede, a natural satellite of Jupiter. It has an ice layer in white, a silicate mantle in brown, which is solid, and most importantly, a liquid iron core in gray, whose size ranges between a fourth and a third of the radius of the planet. And Ganymede generates its own magnetic field, but we know it's not just due to thermal convection because the heat emanating from the core is insufficient compared to the adiabat. So we're looking for other sources of motion of compositional origin. And what I want you to remember is this very simple thing. You've got mostly two elements in Ganymede, mostly iron, and another lighter element, which we believe to be sulfur, because it was abundant in the protosolar nebula and because it is very siderophilic. So it can easily be trapped into the liquid metal. And we just need to understand how these two components behave with pressure and temperature to understand what iron snow is. So once upon a time, Ganymede was extremely hot, meaning that everywhere in the core, the temperature was above the liquidus. So all the metal was molten. But the planet cooled down with millions and millions and millions of years until at some point, locally, the temperature was below the liquidus, so that solidification of the metal could start. And I insist, crystallization starts at the core mental boundary and not at the center of the planet as it happens on Earth, because the slope of the liquidus is steeper than the core temperature. The snowflakes which appear are made of pure iron. Whereas I said before that in the liquid you've got iron, but also sulfur. So it means that the density of the snowflakes is larger than the fluid. And because of that, they fall because of gravity. And you've got a snow zone developing. Consider that the dotted line corresponds to the bottom of the snow zone. If the snowflakes try to fall past it, they enter the region where the temperature is above the liquidus, so they have to melt. And now you have accumulation of molten snow at the bottom of the snow zone. Now this snow is extremely concentrated in iron when it melts. So it means that its density is larger than the rest of the fluid, and in particular, what's underneath. So it's like having a layer of water on top of oil. It's unstable, and this leads to compositional convection. So many motions inside the planet, but it's not enough to conclude you have dynamo. These motions need to be at large scale, sufficiently fast, and a necessary but not sufficient condition for dynamo is that the magnetic Reynolds number should be sufficiently large. So numerical simulations have been performed to see how compositional convection can lead to a magnetic field. And they successfully got the appropriate order of magnitude of the magnetic field and the appropriate shape. But the problem is they are based on a buoyancy flux coming from the snow zone, which is absolutely unknown because the physics of the snowflakes crystallizing, falling, and melting has never been modeled. So from simple models, we get values similar to what you have on Earth, but the phenomenon actually doesn't happen on Earth. And because we don't know the buoyancy flux, to be simple, we consider it constant in time and space. So we need to verify these assumptions. And for that, we need to study what's happening in the snow zone. Additionally, you have motions in the snow zone, which can further contribute to creating the magnetic field or modify its shape. Because you've got the snowflakes which are falling and which are displacing fluid. And the perturbations they create are going to propagate as internal waves, inertial waves because of the rotation of the planet, and internal gravity waves because of the stable stratification of that layer. Okay? So to begin with, forget completely about crystallization, melting, and compositional convection, and just consider that in the experiment, I want to look at snowflakes falling in a fluid, and I want to see what's the motion they create. I want to see the physics of the flows produced. So the analogy is that instead of having liquid metal, I have some water in a tank, and instead of having iron snowflakes, I have spherical glass beads. And I insist, I want to look at the motions created by the particles themselves. So initially there is no motion in the tank and I need to release particles without initial velocity. So to do that, I put them into a cylinder with some water and some rhodamine, which is just dye colored in orange. And I seal the cylinder at the bottom with a latex membrane, which is stretched. And what I do initially with the needle is I puncture the membrane in the middle. It quickly retracts and releases the content of the cylinder. Note that you will have a difference between the motion of the particles and the fluid because particles have inertia, quantified by the Roos number, which is the ratio of the settling velocity of an individual particle over reference velocity for the fluid. And this is nothing but a free fall velocity of an object whose size is given by the size of the diameter of the cylinder, its diameter, and whose initial density is prescribed by 1 gram of particles inside the cylinder. This mass never varies between experiments, it's constant. And so when you have very small particles, they have low inertia, low Roos number, and their motion is very similar to that of the fluid particles around them. But when particles are very big and have a large inertia, large Roos number, their trajectory is extremely different from that of the fluid. So to see the difference, I need 2 filters. I have a camera with a green filter to see only reflections and refractions of the laser sheet by the glass beads, so I can only see the particles. And I have another camera with an orange filter to see only the coloring, rhodamine, which is caught in the eddy, so I can track the turbulence and make a clear difference between them. And then the whole setup is on a rotating table, so I can study the effect of planetary rotation. So what I do is I systematically vary the size of particles from 5 microns to 1 millimeter of diameter, the rotation rate of the table up to 20 rotations per minute. And then I do every experiment several times because of sensitivity of turbulence to initial conditions. Okay. So I'm skipping this. And so this is typically what you can have in the experiment. You've got a cloud which is falling and you have particles and rhodamine. And thanks to the goggles, the 2 filters, you can make a clear difference between just particles on the left-hand side and just rhodamine on the right-hand side. Okay. So let's see what we have in a still ambient to begin with. And for a start, forget about the complexity of particles not having the same motion as the fluid. Consider now that the mass excess of 1 gram is due to salt water falling in fresh water. In the lab, it looks like this. So what you see is a cloud which is decelerating and linearly growing in depth. And actually, it's been studied a lot in the literature, and it's been modeled in 1956 by Morton under the name of turbulent thermal. And what I just want to remember from its model is 2 things. Basically, what's falling can be approximated as a sphere. And since the sphere is open, the turbulence which develops inside is responsible for an inflow of ambient fluid into the sphere, which is called entrainment. And the velocity of entrainment at the interface VE is proportional to the only characteristic velocity scale of the problem, which is the velocity of the cloud falling, Z dot. Alpha, the coefficient of proportionality, is called the coefficient of entrainment, and it is nothing but the growth rate of the cloud index, dr over dz. As you can see with an average of different photographs of salt water during the experiment, you can see that the growth rate is constant and within a clear range according to the literature.
What's the Reynolds number of the flow on the scale of one of these particles?
Oh, during the experiment?
Yeah.
It's going to be between, so quite small, lower than 1, I can't remember, up to 150 for the largest ones, the particular Reynolds number.
So it's okay. The smaller ones you could just treat by Stokes drag, right? And you're back
exactly.
to the homework problem of sedimentation, right? But I mean, the interesting cases are the large Reynolds number.
Yeah. But we're going to see that because they create a turbulent flow and behave collectively, when they are small, it's also quite interesting because we've got more turbulence. You're going to see that in a moment. Okay. But it's true, I've got a Stokes velocity for the smallest ones. So it's a very clear reference frame, okay? And we can see now how different it is when you have particles. So for very small particles, which have very low inertia, the agreement is quite nice. You have a small difference, and so you can define a coefficient of entrainment. But the larger the Roos number, the less clear. And actually, when particles are too big, you can't define a coefficient of entrainment anymore. And this is now due to a quick decoupling between the turbulent eddies at the top and the particles underneath, which are falling too fast, as illustrated here. What you see in white is the particles, and what you see in orange is rhodamine. And from left to right, the particles are larger, so they have more inertia. And apparently, the more inertial they are, the earlier the decoupling. although this phenomenon of separation between turbulent eddies and particles is actually a gradual phenomenon, as you can see in the middle. So what I can do is, for all my experiments, when I see separation in my field of view, I can record the depth where it happens, and then I get the following measurements. And to understand this trend, we need to define separation. So just basically, if you have an heavy object outside in the wind, it wants to fall, but if the wind is blowing super fast, it can sustain it. But if now the wind is decreasing in velocity, the object is going to fall. It's exactly the same physics here. As particles want to settle at their settling velocity, so if the cloud is falling faster and eddies are moving faster, it can sustain particles. But if it decelerates too much, particles will try to settle faster than the cloud is moving downwards, and there will be separation. So a basic criterion for separation is to say that the velocity of a single particle is equal to the cloud velocity. And just injecting this into the equations of Morton gives you that the depth of separation scales as roots to the -1. So you have a clear separation between two regimes. The first regime in red is linear growth of the cloud, which is turbulent. And then you've got separation, and then particles fall vertically, approximately with a constant velocity. This is the swarm regime. I want to focus on the first one. And what I want to see is if I have the same growth rate for my particle clouds as salt water. So what you see here is the entrainment rate of particle clouds divided by the reference value for salt water. So 1 is the reference in ordinate, and the red hatched area corresponds to the error bar on the measurement of that value of reference. And so for the clouds, we have 3 main conclusions. The first one is that you've got a drastic decrease of entrainment for the largest Roos numbers above 1. This is due to the very short-lived turbulence forcing, because these heavy, big particles decouple from the turbulent eddies very quickly, okay? For the rest of the clouds, 2 things. For the same experimental apparatus and releasing the same mass excess, particle clouds entrain more than saltwater clouds. And you've got a local maximum of enhancement for a finite inertia for a Roos number, which is close to 0.3. So if you want to understand that, we can look at the flow. So what you see,
as the particle drops, does it reestablish an entrainment turbulence cloud?
After separation?
After it separates, yes. I mean, somehow it seems like what's going on is the object of the particles is separating from its weight.
Yes.
Which is somewhat amazing. And the question is, does it reestablish a new weight if it falls long enough?
Yeah, so I understand. I can just tell you that in the experiments, no. The main thing you can observe is that when you have sufficiently small particles, sufficiently large to separate, sufficiently small not to, so that they are sufficiently numerous, they create a laminar flow, but not a turbulent one.
But they do, I would think, establish a laminar weight. They must.
Yes.
Okay.
It is the case. Yes,
Okay.
they create a macroscopic.
So the point is, you separate from the turbulent weight and establish a laminar.
Yeah.
Okay.
So here you see an average of different photographs, so you have an idea of what's the trajectory of the different particles. And so what you see is that particles preferentially concentrate on the periphery of eddies here and there. So this is an effect of preferential concentration, which is well known in the literature and which is due to the fact that these particles are denser than the fluid. And the second thing is that you see that they only fall on the periphery where you have downward velocity, which is called preferential sweeping or fast tracking. And so due to that, if you look at the schematic here with the white arrows, you can see that the buoyancy force of the particles always has a positive work. So they are always forcing a flow for a Roos number close to 0.3. Whereas if you have very small particles or salt water, you've got particles everywhere, and in particular, going back up on the edges. So it means that you have to convert some of your turbulent kinetic energy into potential energy just to lift the particles on the edges, and there the work is negative, so the forcing is less efficient. Additionally, it means you have a larger concentration here and there than what you would have if particles were everywhere homogeneously distributed in the cloud. So here the forcing is more efficient, and also because particles are closer, through drag, they are more capable of forcing the flow by two-way coupling, by really prescribing their own trajectory to the fluid as they do initially, and they create the turbulent flow. And this is illustrated here. You can see that particles want to escape from one vortex and just settle vertically, but actually they are so concentrated that they are capable of creating another vortex. And in some movies, I can see a small third one. So you have like this, a small cascade of vortices, which keeps entrainment longer lasting and probably more intense. So it's a quite interesting observation. which calls for further experiments in different configurations. There have been configurations with plumes, so in a steady regime releasing particles, but it wasn't observed possibly because the Roos number was close to 0.3, but also because, so that's probably the main reason. And it could also be applied to typically gravity currents, so avalanches, landslides, pyroclastic flows, where you have an interface between turbulent and non-turbulent flows with particles. It can modify the entrainment. Now we can see what we have in a rotating ambient. And again, we begin with what's simple, so just salt water. What you initially see here is that the cloud is linearly growing in depth, but then very quickly you can see it's creating a columnar flow, and maybe you manage to see that there is rotation. So at some point, everything starts spinning around the axis of rotation. And this transition for salt water also holds for the particles. Here you have no rotation, and now you're spinning at 10 rotations per minute, and you can see that particles are trapped into a columnar flow. So actually, it's very well understood from the literature on saltwater clouds. Initially, the cloud is small and falls very fast, so it's dominated by its inertia, whereas in the end, because it decelerates and grows, at some point, the Coriolis force is going to predominate on its dynamics. And you expect a transition between the two regimes to happen when both effects compare, so when the Rossby number is approximately equal to 1. So what you can do in the experiments is when you see a change in the morphology of the cloud and you see rotation which starts, you can compute the Rossby number and verify that it is equal to 1 for these clouds. Again, we have some exceptions for Roos numbers larger than 1. This is because these particles have decoupled from the fluid and behave as swarms, so it's another story, okay? But so for these clouds, 2 regimes, and we can study them separately. In the first phase, you can be very caricatural and just say that, okay, you've got just inertia, you completely forget about rotation, it falls fast, it's turbulent, it's entraining ambient fluid, so it's linearly growing, and we're having exactly the same thing as before. And actually, it's not the case. If you look at what you have at 5 and 10 rotations per minute, you have nearly no sign of enhancement of entrainment here, and you have absolutely no sign there. And so a way of understanding it is that, okay, this cloud is dominated by inertia, it's entraining ambient fluid, but in the outer conical shell of the cloud, rotation is playing a part. It is going to change the direction of the flow because of the Coriolis force, so that the eddies, which you could see in the laser sheet, which were horizontal, are going to tilt at some point and align with the axis of rotation. And because of that, you cannot have all these effects of preferential concentration and preferential sweeping anymore. And so the flow is dominated by inertia, it's turbulent, it's entraining, but just as salt water because you don't have any particulate effects. And another interpretation to be confirmed with numerical simulations is that the centrifugal force in vortices seems to be comparable to the centrifugal force due to the rotation of the tank. And so this can also inhibit the particulate effects, and so you can't see anything anymore, at least above 5 rotations per minute. In the second regime, the main observation is that the faster you spin, the narrower the column. You can see it with a superimposition of different photographs. And it's confirmed by the measurements. If you calculate the width of your column with a standard horizontal deviation, you do verify that if you spin faster, you have a narrower column. So actually, it's not due to what's happening in this regime, to be rigorous. It's due to the transition between the two regimes. We said that transition happens when Rossby equals 1, so it gives you that the depth of separation scales as omega to the -1/2. So if basically all your clouds grow at the same rate, you get that if you spin faster, the depth of transition is lower. And so just from geometry, you have a narrower column which is developing. And if it always contains 1 gram, it means that this column is more concentrated than the others. Its effective density is larger. So the front velocity of the column, which appears to be constant, is larger. And this is verified with measurements. From white to red, when you spin faster, you can see that the column is developing faster in time. Okay? But this conclusion only holds for the front velocity. What's interesting is that it's not true for the rest of the particles. So we've got particles falling without spinning and then spinning at 10 rotations per minute. I would like you to look at the intensity recorded by the camera in time. So it's a Hofmöller diagram. What I'm doing is I'm taking a photograph, averaging information horizontally. So I just get a vertical profile of light intensity. And then I look at the different profiles in time. And so what you see is that you've got a cloud which is decelerating because it's convex, it's growing, but after 25 seconds, you can't see anything anymore in your field of view. No particle. And now when you're rotating, you've got a bright blob falling super fast with a constant velocity here. It is that guy at the front. But then many particles are left behind and take a huge amount of time to settle, even after 25 seconds. So it means that inside a planet, the residence time at a given depth of a particle, which is in the bright blob or the stem, is going to be very different. So their thermal and chemical equilibration with the ambient is going to be altered by rotation, depending on the intensity of it, depending on the Rossby number. And actually, if you want to go even further on geophysics, what you can do is to try to distinguish different regimes from everything I've shown. So the first transition we saw was from a regime of linear growth and turbulent cloud to then separation and falling vertically. It can be computed from a local Roos number. So now it has a star. It's comparing the settling velocity with the local cloud velocity. And initially that number is lower than 1. When it is equal to 1, you've got separation, and then you've got vertical settling. So we can see it with the different sizes of particles in abscissa. So again, it's the Roos number. So it's the proxy for the size of particles from 5 microns to 1 millimeter. And you've got depth inordinate from 1 centimeter to 10 meters. I can go beyond the size of my tank, which is 1 meter deep, because I'm using the equations of Morton. So if you take any size of particle, let's say Roos equals 10 to the minus 1, the cloud is expanding, expanding, expanding as it falls. And then at some point you've got separation and then vertical settling. Okay. Then the next transition between regimes I'm interested in is the fact that in geophysics, you can find in papers that some people are reluctant to say that snow is going to move the fluid because snowflakes falling are not going to produce much flow. It is true that if I do this experiment with 1 gram of particles in the Pacific Ocean, they won't be interacting and you will just have some particles falling alone. So if you look at the literature on Rayleigh-Taylor instabilities based on suspensions of particles, you can see that particles can have a fluid-like behavior and develop the instability when they are sufficiently close to interact through hydrodynamical interactions by moving fluid around themselves and around one another. So to compute this, to have a criterion to determine whether they behave collectively, you get a dimensionless interparticle distance. And so basically when particles are very close, the ratio is lower than 1 and they behave collectively. But when they are too far away from one another, they behave individually. I just need to know the reference length scale lambda, which is the typical length scale over which I expect one particle to move fluid around itself. So if you look at the flow around a particle at very low particle Reynolds number, you get that the inertial screening length on which the flow is changed scales as it's a diffusive length scale based on the settling velocity of the particle. If you increase the size of the particle, you now see that actually deformations of the streamlines happens rather on a size which scales like the size of the particle itself. And if you even increase further the size of the particle, now you have wake effects, but just basically you can say that the wake close to the particle scales as the size of the particle itself. And so to be general, you can say that in this range of Reynolds numbers, lambda is the maximum between the inertial screening length and the size of the particle. And so just from this, you can compute the moment when h is equal to 1. And so now you've got a separation of both regimes in 2, okay? Either the cloud is expanding and particles are sufficiently close to interact or not in the blue regime, or you've got a column which is developing, and this is what you were talking about. You've got separation, but if particles are sufficiently close to one another, they are interacting together and you can clearly see a laminar flow which is developing as they are dragging fluid downward. But if they are way too far from one another, you won't see that effect and you will just have individual wakes at most, okay? So if you believe that snow is not going to produce a flow, you are right if you're in the yellow regime. But in any of the other regimes, the snowflakes falling are going to produce a flow. Either it will be laminar or turbulent. So it needs to be investigated in the geophysical application. Some things can happen in the snow zone. All right. Another step, if you want to go even further on the geophysics, is to do numerical simulations. And actually, initially, my experiments were thought as test cases, which would be like very clear experiments with a certain physics, which we would need to model with numerical simulations. And once the model worked, we could do these simulations at a planetary scale. So if you want to do that, you can't use Lagrangian simulations because the cost would be too much. So I'm modeling the particles as a field of concentration. If you want to do that, you need to keep mainly 2 ingredients. The first one we saw is the fact that particles do not move as the fluid because of inertia. So if you write the momentum equation for a particle, it's undergoing buoyancy and drag. And if you want to just consider, it's the simplest model, the fact that particles very quickly respond to the flow and align with it, So it means that tau p goes to 0. This just gives you that the velocity of a particle is the velocity of the fluid, so it behaves as a passive tracer, plus a constant settling term, okay? And once you know that velocity of the particle, you have to advect your field of concentration at this velocity. The second ingredient is just the fact that particles are creating the flow from the very start. It's two-way coupling. So they need to force the flow in the Navier-Stokes equation. So you just have the Coriolis term if you want to take into account rotation, and forcing is going to be this external term. If you write it in the continuous approximation, if you say that you have a field of concentration, this term is proportional to the concentration in particles, which is consistent with everything we've seen before and with our everyday life experience, okay? So it's extremely simple. It's very basic physics. It's the minimum physics to model this, but actually it very nicely captures most of the experimental observations I've shown you and even others. So, oui.
Would you need to add in the Navier-Stokes a force of added mass?
It's a good question. Why are you asking? Why are you asking?
Because I thought at some point, well, the correct answer is probably you need it, but maybe it's negligible, and how much that impacts the dynamics.
Yeah, I don't know. I don't know at all. It's seemingly, so it's capturing most of, so you can see that after separation, and that's why it just looks like this. This is what you saw at the very start of the presentation on the right-hand side. It captures even this flow. So then I would need to compare the velocity field, which is developing the experiments and the numerical simulations, so in experiments with PIV, to see that, because then I guess that in this regime, I could be sensitive to that, but otherwise in the turbulent regime, I'm not so sure. And then to better catch the physics of the particles being on the side of the eddies, etc. My guess is that from reading the literature on particles in turbulence, I would need to take into account the path history term. But added mass, I don't know if it's an important effect or not. I have no idea.
I would guess that at least you would see deviations due to that term, especially when the particles keep clustering together and you're not in the individual regime. So
yeah,
maybe that extending that will give you an indication of how much that is required to match your.
Yeah, it will probably play an important part for the largest particles, because here, so I'm going to ρ equals 0.8, but actually this model is based on ρ's being much lower than 1. So it's not appropriate. So basically, so probably here it's saying that particles behave collectively, and that's why you can model them like this, although it's not the case in the experiment. So yes, I guess that, yeah, for the largest particles, it would make a big difference. And so what you're looking at is just one example. It's the one on the entrainment coefficient we saw before in the experiments. And so what you're looking at is 3D numerical simulations, direct numerical simulations with volume of fluids using Basilisk. And what you see is a cross-section, vertical cross-section in the middle of the computational domain. And I superimpose at different moments the field of concentration. And I'm not interested in the color. I just want you to see the morphology of the cloud and see that you've got an optimum of entrainment here for a Roos number, which is close to 0.3, which is exactly what we had in the experiments. So the agreement is quite nice, although the physics is really reduced to the minimum. And if you want to go to a next step, what I'm presently doing, so this is recent work I've been doing, is to take into account melting of the snowflakes, because at some point I want to model this and get that compositional convection inside the planet. And so melting is complicated in experiments to handle thermal effects. So what I'm doing is dissolution of sugar. And if you use sugar in water in the laboratory, you can't see much apart from changes of the refractive index. So if you want to really see the flow, what I have to do is to cook my own sugar. So I'm really cooking it, adding rhodamine inside. Then I let it dry, I crush it, I mix it to get different sizes of grains, which can be sieved. And so then I get different ranges of particles, which are very clear. And what I can do is pick a range of particles and sieve it above water. So that's the principle of the experiment. So it's sieving at a constant rate. You can visualize what's happening in the laser sheet. And so you can see the grain falling, but most importantly, and this is why I wanted coloring inside the grains, as it is dissolving throughout the path, you can see the buoyant water which is left behind, the sugary water. So everywhere it is orange on the photograph, it means that there is sugar in water, so it's going to fall because of buoyancy, because sugary water is denser than fresh water, okay? And so we can visualize this with a camera, and we can try to look at the flow, but I think it's not gonna work. Wait, okay. So what you're looking at is grains of sugar falling over 20 centimeters. Initially, they are just falling, but very quickly you can see a wavelength appearing, which corresponds to a linear Rayleigh-Taylor instability, which is less and less linear, more and more mixing. And now you've got the appearance of a macroscopic recirculation, which is strangling that dissolution layer and creating a massive laminar plume, which is taking the grains towards much larger depths. So I can play it again. So that's typically what you can see in the experiment. It's quite interesting here to see that when you're sieving uniformly on the 20 centimeters, you get a very non-uniform flow, which is developing with a non-uniform buoyancy flux nourishing the compositional convection in a shape which is very reminiscent of what you have underneath some clouds, thunderstorms and cumulonimbus clouds. And actually, it's an analogy which is quite interesting because the physics is extremely close to what we have. So, okay, no, up. So first, I want to insist on the fact that in the two cases, there are two things which are driving the flow. When the particles are falling, so you can see them in red in that rectangular area, here you've got drops and possibly you could have snowflakes. So this is a microburst over the city of Phoenix. You can see it's quite violent. And so what you're visualizing is mostly drops. So the settling particles are imparting momentum, kinetic energy to the fluid, and this is driving the flow. That's one thing. And the other thing is that because of dissolution here because of melting or evaporation, they're imparting buoyancy or potential energy to the fluid. And this is going to drive the flow, okay? Two ingredients, and it's quite important to make a difference between the two of them because actually they can play together on driving the flow. One can clearly predominate on the other, and sometimes one is acting against the other. So on the literature on downdrafts, which is kind of what you're looking at here, you can see that sometimes when the air is reaching the ground, you've got so much compression of the air that it gets so hot that the buoyancy of the air is positive, but you've got so much precipitation that it's overcoming that positive buoyancy, and overall you've got something which is going downward, okay? So in that case, you've got an opposition. And so it enables you to distinguish basically two types of flows in the atmosphere. So you've got like a wet downburst, so wet because you've got sufficient precipitation to be above a certain threshold. So this is what you saw. But actually the flow can be completely driven by the fact that my grains of sugar are going to dissolve and I just have buoyant water without snowflakes reaching the bottom of the tank. And this corresponds to dry downbursts. So you can't visualize the column because there is no water, it has evaporated. But you can see that there is a downburst because you've got violent winds which are taking dust very far away with large velocities here, and they're blowing leftward. Okay, so which is a distinction which is quite interesting. We've got the same thing in the lab. So I'm being quite drastic to show the difference because I'm changing both the mass rate and the size of my grains to show you that. But here, basically, you can see that the snowflakes are so small and the mass rate is small that the snowflakes hardly reach the bottom of the tank. Whereas here they are really driven towards large depths. This is the movie you saw before, but just accelerated. And so it's quite interesting to investigate what's driving this physics. You have to know that in geophysics, because this is already very complicated, we consider nowadays that melting of the snowflakes is instantaneous at a given depth. But so from this, you see that even in the first regime, when you had that layer developing before the instability and the laminar plume, you have a finite width of the mixing layer because you've got a finite rate of dissolution or melting. And so if you want to look at this, you need to take into account the drag of the snowflakes, that's the first ingredient, and the dissolution or the melting of the snowflakes, which is a very interesting nonlinear physics. The size of the grains is controlling their settling velocity, even in the initial stage. But then as they are shrinking because of dissolution, that velocity is going to change, but it's also going to modify the density of the fluid, which is increasing. You've got saturation. So it's reducing the buoyancy of the snowflakes. So it's reducing the velocity at which they fall. And therefore, because you have a lower buoyancy velocity, you can see that you have less advection around your grain of sugar, which is taking away the saturated layers of fluid. And so it's further going to decrease the size of the particle. And it's also going to alter the rate of dissolution because of saturation. And if you add stirring, it's even worse. So it's a very non-linear physics, which can be taken into account appropriately if you take into account the settling velocity of the particles, their size, and the dissolution rate. So we need to take into account a whole population of grains of different sizes. And so if you want a continuum approach, you have a PDF to be taken into account. But inevitably, this will call for simplifications because it's exactly the same challenges they face in meteorology even nowadays. If you want to model this at a planetary scale, you can't keep that over large time scales and length scales. So it calls for simplifications, and this is what I need to indulge into now, presently. Thanks for your attention.
For questions? Yes.
I mean, really interesting. The jet lag maybe setting up these things. Right. It's just, I mean, kind of following up on this point. I mean, if I think back to the beginning of the talk, you're saying that this was all observed by crystallization of, iron. So really, that crystallization happens on some range. I mean, is there enough known about that process to say, okay, I'm going to likely, my PDF of what size of the snowflakes I'm going to make is something that I'm going to always be in one or more of this particular regime, so that it's okay to say, I'm always going to this or that regime, but I'm going to spread it across different regimes.
Yeah. Unfortunately, nothing has been looked at on what's happening in the snow zone, and in particular on crystallization. And it's not something I've worked on. So I have absolutely no idea on what's going to be the size of the snowflakes, what they look like, and where they develop exactly in the snow zone. And so even if you want to take into account the different regimes I talked about, I don't even know what's the initial size of the turbulent cloud I'm looking at. So we've got the core mantle, possibly, so homogeneous nucleation in the bog is very complicated. So probably what's going to happen, okay, boom, let's go to the beginning. Probably what's going to happen is that you will have crystallization at the core mantle boundary. Well, this is the simplest case. So there, and this is not spherical. You've got a certain wavelength, but if you read the literature, you've got so many wavelengths and few data to really be sure about what it is, that the best thing I can do so far is just suppose I've got a certain wavelength, that's the initial size of the cloud. And for the size of the particles, it's an unknown, and I need to vary it and see how it affects the flow.
Just basically another thing the way you presented it, like all the experiments and models, like, okay, I have a bunch of particles I draw and I see what happens. That obviously this is sort of a continuous process of crystallization. So I'm just trying to think through what would change, like if we go from like that single burst to kind of kind of continuous process. So I don't know. Again, maybe there's not really anything known about the expectation that you're mostly laminar with columns of turbulence and stuff, or like are you getting enough crystallization that it's all what changes?
Yeah, I'm not so sure. So on the literature on plumes, I said that they've looked at the flow. Basically, you have a plume which is developing. Now you would need to see what's happening in a stratified environment, because the snow zone is stratified. Similarly for my flows, and so I don't know in particular what it's going to look like. But is it continuous? So should I look for a steady flow of snowflakes crystallizing and falling? It's not even sure. There have been some experiments which were done at IRFE by a postdoc called Ludovic Huguet, trying to model crystallization of iron snow in his experiments. And what he saw is that actually you've got crystallization which was episodic. And when it happened, you had many snowflakes which were created and falling super fast, and then nothing happening for a large amount of time. And if I'm not mistaken, this was due to supercooling. And so because of that, it can be episodical. But I don't really know. It's completely open. I've done that, but if I want to apply to geophysics, I will take into account the steady state, because I do believe that it will be important.
So a question, then there's a follow-up, which will make the reason clear. Have you explored what would happen in this process if you had a pre-existing state of turbulence that this was injected into?
No, I haven't.
Well, the reason I asked is, I mean, listening to this, it seems very relevant to the problem of planet formation, which, right, is the problem of sedimentation of dust grains in an accretion disk. So, I mean, and these things are bloody heavy, right? They're several thousand times heavier than the ambient, more dense than the ambient gas. So it seems a close analogy. So, and the key difference, of course, is that, I mean, if you believe any of the stories, that's going to be going on in a turbulent environment that is, you know, it is responsible for the accretion process.
Yeah.
The magnetorotational instability or any of these others.
Yeah.
And the theory, such as it is of this, is treated as sort of simple sedimentation. You know, the sort of things that you see in a textbook and so forth, with none of these collective interactions that you're talking about, which would seem to make it quite a significant difference.
Yes.
So, I mean, have you thought at all in that direction?
Not at all. I didn't think about it, to be honest. Yeah.
It would be a good thing to do.
Yeah. Yeah. I will look at it. Yeah. But yeah, I haven't. And so I guess many aspects will be similar. Probably like the thermal developing will be quite different.
Yeah. And you certainly will have rotation.
Yeah.
So in terms of your original motivation, how is it known that Ganymede generates its own field for sure?
It's been measured by a spacecraft, the Galileo mission in 1996. And so they...
Well, that's that it has a magnetic field.
Yeah.
Yeah, how do you know that it's self-generated? How do you know it's not in the...
And so they know it's not from Jupiter, and they clearly know it comes from inside. And actually, because all the contributions from the exterior have been subtracted, so they know, apparently for sure, that it comes from inside the planet. It's not coming from induced, well, it's not induced by another external field, because apparently they can subtract that as well. It's not coming from Jupiter or the other satellites around.
I mean, I don't
and so the details of how you can be sure it comes from there, I don't really know. Well, I can't remember. It's written in the papers, but I don't remember. But then actually the main question about that, what they're wondering about is it due to dynamo? And that was also, it seems to be solved in 1956. It seems to be admitted that if you take into account a subsurface ocean, which would be conductive and moving sufficiently fast to generate a magnetic field, it's not plausible because you would need to move super fast. And remnant magnetization is not enough either. And then it's considered like almost granted that it's dynamo. And the simulations nicely reproduce exactly, well, extremely close the value of the magnetic field and its shape. But yeah.
I mean, you could imagine even the Jupiter field is weak. I mean, it's moving, it's winding it up, isn't it? It's quite clear that you can just subtract. Well, maybe it is. I don't know. To me, it's not quite clear you can just subtract.
Completely subtracted from the measurements.
Yeah, I mean, because you don't know now. Unless it's a geometric thing that says that if you were winding up the Jupiter field, it wouldn't look like the Ganymede field. But you could generate quite a strong field from a weak seed field, from a weak imposed field from Jupiter.
Yeah, I haven't checked how they do that.
And another question. So in how rotationally constrained is Ganymede?
I don't remember the value. All I can tell you is that my experiments at 5 rotations per minute, but I don't remember the value, but my experiments at 5 rotations per minute corresponds to the upper bound for Ganymede. And so it means that every time I'm spinning faster, it's actually too much. And what you saw when I was showing movies at 5 rotations per minute, it corresponds to the upper bound for what we have. But obviously, so the reason why I have a range of Rossby numbers and why I don't remember the value is because you need to know what's the length scale on which you want to compute it. And I don't really have a length scale for a cloud inside Ganymede. And I can take the size of the core, but then it's extremely different from the physics I'm showing.
You need to show, presumably, if your Reynolds number on some scale, maybe a cloud scale, is hundreds, I guess, drive it down.
Yeah. So it's again the question of, I don't know what's going to, if there are thermals, particles settling clouds like this, I don't know what's going to be their size. And that's the reason why I haven't shown you the different regimes of behavior of the clouds on Ganymede, because I can do all the computations if I know the size of the cloud, the initial one, but I don't know it. And so then I end up just doing multiple graphs depending on the size. Then, well, it's a bit complicated. Or the message is not very strong, and that's why I'm not showing it.
So I was going to ask about dust in photoplanetary panel. We were also worried about coagulation and fragmentation. Right? So you started with the same size of particles, but do they stick together, grow in size, or break up?
Not at all. So it's something I didn't want to have. So to simplify the problem, so it's absolutely not something I have. So I have actually, what you've seen is both monodisperse and polydisperse and bidisperse distributions, but it hardly affects the regime of turbulent thermal. It affects the regime of swarm afterwards. But coagulation, no. It's been done, if you're interested in this, fairly close, it's been done with liquid metal in oil by a former PhD student in the team, Jean-Baptiste Wachel. And so you can look at his clouds and he's got the drops developing and coalescing and breaking up. But this is not something I have at all.
Well, I think we're right on schedule. It's been a very interesting morning. Let's thank Kriaa again.